So we're going to talk about 2 more small sections, and then we're done with new stuff. There was supposed to be a homework assignment due today, as you noticed, but I forgot to post the video until late. I didn't post it yet, I just haven't done it. And so if you don't have your homework done, you can turn it in until Thursday. I'll check my box at 1 o'clock and then give them to the grader, and I won't take off any points. So turn them in by Thursday. There is an assignment on this, and that is due on Friday. I'll say it loud so you know, okay? It's 6, 7 problems, it's not long. And then on Friday in class, we will, I'll give you the final that I gave, and we'll just start going over it. And then we'll finish it together. You can finish it on your own, and I'll also give you a set of 25 review problems for the final that I'll pick some subset of those, something like that, to go on the test. Your final's on Monday. I've already given you extra credit 3 times.
I know, but
No, I was reason
that.
that.
Do a good thing, right?
That's true. Okay.
Can you get a piece of paper?
Oh, yes, you get a piece of paper for the final. Yep.
Do I have 2 pieces of paper?
Can I think on it? Okay, let me think about it. I don't actually think you need 3. I don't think you need 2, but let me just think, okay? Okay, so here's our motivation. Suppose you toss a 6-sided die 60 times. How many times do you expect each of the numbers to occur? 10. Okay. Is it going to happen that you always get 10 of each number exactly? No, but it should be kind of close-ish, right? Yeah. And one question you might want to ask is well, how far away from 10 in each category is far enough away that your die might be loaded and somebody's cheating you? Is that a good question?
Yeah.
Okay, that's what this is going to answer. So suppose you suspect that particular die is unfair. You're interested in testing the hypothesis, H0. The die is fair. That's nothing going on, right? HA versus the die is unfair. You take that die from the crooked dealer and you toss it 60 times and you record the number of times each number shows up, and you create a table of expected counts. What's every expected? You're going to have this table, and you're going to have the numbers 1, 2, 3, 4, 5, 6, and then number expected. How many times do you expect to see each number? So you have a 10, a 10, a 10, a 10, a 10, and a 10. And then suppose when you toss it, you get 1 of those, 13 of these, 15 of those, 10 of these, 11 of these, and how many 6s would I have to have then? Crap. How many tosses did I do? 60? Is that right? If I put a 10 there, does it add up to 60 as well?
Yeah.
Okay. Is it clear why the expected values are all the same? Because you expect them all to be a fair thing. And then can't we do a chi-squared test on this thing? It has how many rows? 2. How many columns?
6.
6. Okay. And so this 2-way table of expected counts, each expected count will be 10 in this case, and the observed counts are from your tosses. And then you find the chi-squared statistic, just like we did in the last time. And if you've got a big chi-squared, what does that mean about your p-value? It's going to be small, and you can conclude that the die is unfair, and that you should get a new one. Yes?
So on the homework, we had that one problem where we multiplied everything by 5.
Yeah.
Is that something we could do in a real statistic, or should we, do it 5 more times?
That would be assuming that your 5 more times resulted in the exact same thing, which probably it wouldn't. Does that make sense?
Yeah.
That assumption on the homework question was that for some reason you just had a status set that was this thing just scaled up by 5. And so definitely if this thing scaled up by 5 happened, there's a lot more evidence that your die really isn't fair. But probably some variability, like as crazy variability as this, might even occur with a fair die. Yeah.
Wouldn't the goal be to, for multiplying it by 5 to see that if you had a larger sample size, could it be possible? So you would then make it.
It's possible. Yeah, definitely. So I guess you could kind of ask that same question, like if you observe this thing but times 5, then would you reject H naught? And the answer probably would be yes. Yeah, definitely. Okay. So in this example, these expected counts were all the same because every event had equal probability. That's not always true. Like suppose, for example, the thing that I have. So this is what we're doing today, this thing called chi-squared goodness of fit. And what this is referring to, goodness of fit asks how good are your probabilities? How good do they fit? Which I know is like horrible English, okay? But like how well does the assumption of each probability being 1/6 fit? Does that make sense? Like does it fit well or does it fit poorly? So for example, there's some speculation that certain numbers might be more likely at the end of a lottery number. Like on the very last digit, like maybe some numbers more likely than others. And if you wanted to analyze and confirm that this was not the case, what would the probability of each number being at the end be? 1 in 10th. Because you have to include 0. Does that make sense? And that'd be for each of the digits. Okay. And so when you're working with these goodness of fit things, the first thing that you do is you have to find the expected values, which may all be the same if you have equal probabilities, but might not if you don't. So for example, suppose we're going to test the proportions of people who have certain eye colors, and we say, okay, we think 45% of people have brown eyes, 35% of people have blue eyes, and 20% have some other eye color that's not brown or blue, like hazel or green. And suppose we pick 200 people from the population. How many would you expect to have brown eyes?
90.
How'd you get that?
Double 45.
0.45 times 200 is what you did, right? Yep, which is doubling 45, so that's 90. How would you figure out how many you expect to have blue eyes? Which would be 70. And then other would be, which would be 40. And those numbers should add up to 200. Okay, but the kicker is in this case they're just not all equal, right? Okay. And then the degrees of freedom. All right, so this thing says that for the chi-squared goodness of fit test, the degrees of freedom is always k minus 1, where k is the number of categories for the variable of interest. So let's just figure out what they would be for the eye color and dye example and talk about why it's always this way. So for eye color, how many categories did we have? 3, which would be degrees of freedom is 2, right? How about for the 6-sided die, how many categories were there? 6. So 6 minus 1 is 5. Okay, now the question is does that jive with our degrees of freedom is rows minus 1, columns minus 1 from last time?
Yeah, because columns change.
Yeah. I think I would say row, it doesn't really matter, but one of these guys is going to be 2 minus 1. Does that make sense? Because you have your observed row and then you have your expected row. Does that make sense? And then the columns, you got category 1, 2, 3, up to category K, right? Could be 6, could be 10, whatever, right? So that's why just K minus 1 is always the case. All right. So in these situations, tell me the expected count for each of the K categories. And I think I changed this example on your notes. I said K was equal to 4, didn't I?
Yes.
Yep. And I said that PI are all the same. Right? Okay. So if you have 4 categories and all probabilities are all the same, what is each probability? Go ahead and say it. What?
0.5%.
0.25. Does that make sense?
Yeah, it says 0.5%.
Okay. You said, I couldn't hear you. Sorry.
Yeah.
0.25 for every single one. So for all 4 4 categories, what's the expected value? Is 0.25 times 100 or 25? I mean, I guess one could think about a multiple choice test which has 4 options and maybe A, B, C, and D are all equally likely, right? Okay, so what if we have 3 categories? P1 is 0.2, P2 is 0.5, P3 is 0.3, and N is 100. How many in category 1? 0.2 times 1,000 is 200, yep. How many in category 2? 0.5 times 1,000 or 500. And how many in category 3? 300. And what's one way to check your answer?
Add them up, see if they.
Does that work for this one too?
Yeah.
Because there are 4 25s, right? Okay. And we'll just do one test because this is pretty much the exact same thing as what we did last time. It's not very hard. Okay. So, humans suck at randomizing. I think I've told you this, but this is how you can detect human-caused voter fraud and how voter fraud has been detected in other places, not this country, okay? But sometimes, I don't remember where this happened, and I won't like accuse a country of cheating that I don't know who they are, okay? But you see that 7 is a lot more likely to be chosen than the other numbers, right? And so people have suspected that, say, like an election is rigged, or that somebody like made up voters, and they can go look at registrations and look at things like birth dates and stuff, and they can analyze how often numbers show up. And then if a certain number shows up more often than you think it should, you can conclude that somebody doctored the system by hand. Does that idea make sense? That's one way that things like fraud can be detected. Unless you make a computer do it for you, in which case then you can't see that anymore, right? But humans have done this in the past, I think, and caused problems. I don't know where this happened, but I know it has. So, and the kind of thing that they use to test that is a goodness of fit test like we're doing. So, that's an application of this. You don't think it's just for kicks. All right, so assuming that the students were actually choosing at random, how much would you expect to have for every single category? So there were 190 students, and if nothing is going on, each number is equally likely, right? So what's the probability of each number if nothing is going on? 1 out of
19.
110, yep. And so I'm going to say just expected value should have been 1/10 times 190, which is 19. Okay. So this means that if you were to look at this, you'd expect to see things that were kind of close to 19. And does that appear to be the case? No, right? Not at all. Certain numbers get close to 19, like, 8. I mean, 3 and 4 aren't so far off, and 5 isn't so bad either, right? And even 6 isn't egregious, but the numbers on the ends are terrible, and so is 7, right? Yes? Okay. So state the null and alternative hypotheses. So your null hypothesis, the way to say nothing is going on, is to say P equals 1/10 for all numbers. And HA is that P is not equal to 1/10 for at least 2 numbers. And that's a little bit, it took me a second to think through that and why that had to be the alternative. First of all, does it make sense that it's okay if, so if your null hypothesis is that they're all 1/10, having them not all be 1/10 just means that a few of them could not have probability 1/10, right? But once you have one of them not be 1/10, it forces a second one to also be not 1/10, because the probabilities have to all add up to 1. It's the whole adding up to one thing that means that it's at least 2 of them that are going to be messed up. Like, think that, okay, well, if only this 10 wasn't 1/10, these were all 1/10, that forces this last one to be 1/10 as well. Does that make sense? That's why it's at least 2. Okay? Or you could just say P is not, anyway, but just at least 2, but, could be that only 2. Now to do the chi-squared, we do this sum of observed minus expected squared over expected. And what do you use for every single expected value? 19, yeah. So what's your first observed value? 2 minus 19 squared over 19. Yep. What comes next? Minus 19 squared over, and then etc. 22 minus 19 squared over 19. 21 minus 19 squared over 19. I think you should actually try to plug that into a calculator and see if you can get it to work, because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, give her a shot. And on your test, if I ask you this question, for the love of God, show me your work, okay? Because it really sucked to give you a 0 because you got it wrong and I saw no work, right? You could compute it in pieces.
Okay.
Like, go as far as you can. Does that make sense? Like, if you can do the first 5, do those and do the next 5, like, be a little bit systematic about it.
And then add them.
And then add them together. Yep. And I would show that work too, just in case, something. Also, your calculator probably has an answer feature, right? Like where you can use the previous answer. If you can employ that somehow, that means you won't make a mistake re-inputting something in your calculator. Does that make sense? I should really require a specific calculator for this class so that you're all on the same page and so that we don't have bad systems. Because some of them just, I hate Casios. Anybody get an answer for this? It takes a long time to punch it, I understand. It's pretty big. You want to say? Did you dare? Did you get it, Melissa?
No, I was thinking about programming.
Okay. I don't think there's a way you could program this
I was
in.
actually just looking it up, seeing if there was a.
You could program it by probably having a formula to give. Yeah, I don't think that'll. Anyway, what'd you get?
It's so much
I
nicer.
got 104.316.
Okay, so 104.32.
Yeah.
Okay, that's what I got too. Okay, in the language of chi-squares, that's pretty big, isn't it?
Yeah.
Yeah. Okay, so you think you're gonna have a small p-value?
Yeah.
Yeah. Okay. So look at that table 8.5, 8.4 or 8.5, 8.5 that you got yesterday. What are the degrees of freedom here?
9.
K minus 1, which is 9. Okay, p-value. So look in your 9 category. You have chi-squared is 104.32. Okay, what's the biggest chi-squared you have there? 27.88. So how does your p-value relate to the 0.001?
It's really smaller.
Your p is less than that number. Okay, your part F says, form a conclusion and write it in the context. So what do you do with H naught? So at least 2 of the probabilities are not 1/10. Let's just say we use the alpha equals 0.05 level of significance.
Why is it 2?
Oh, because if it was only one of them wasn't 1/10, then all of the others are 1/10. And because the probabilities have to add to 1, it would force that last one to be 1/10 as well.
Okay.
Does that make sense?
Yeah.
So you have to have 2 of them not being 1/10 in that, for that reason.
So why is it important that you include that it has to be at least 2 if it's gonna happen if there's at least 1?
The same thing, if there can't only be 1.
Right, but what I'm saying is since there can't even be 1, why do you need to include that it's at least 2?
Because it could be 4.
Yes, exactly, thank you. Because it could be more than 2.
Okay.
It could be, there are 2 that are different, it could be 3,
Okay,
it could
I
be
see.
4, it
Yeah.
could be, yeah, at least 2, meaning 2 or more.
Okay.
Does that idea make sense to the rest of you guys? Okay, the point is that 2 is the smallest, that could be different than 1/10, but it could even be more than that. Yeah, because it looks like just from our data, that probably, which ones have different probabilities than 1/10? Probably 1, right? 2, I would say 7 for sure, right? And probably 10, and probably maybe 9-ish, right? Did you buy that? Okay, the other ones all came out to be expected values kind of close to the 19 they're supposed to be, right? Okay. So if you're guessing a number and you want to not, between 1 and 10, and you want yourself to not match your friend, what number should you choose? 1. But now that you all know that, what are we going to do now? Choose 10, yeah, exactly. Don't choose 7, 7 would be terrible. Yeah, you could choose 7 and hope everybody else is the opposite of you, right? Okay. And the last thing I'm going to talk about this semester is some called, this is that, did that, there we go. We're going to talk a little bit about ANOVA. So here is what, and we're only going to hit this very, very, very briefly because we don't have time to hit it more. If you take, are any of you taking Stat 401? No, okay. If you have to take that class, you would learn more about this there, but if you don't have to, I'll just give you an introduction. So suppose you want to compare the mean weight loss for 3 different weight loss programs. So the question you want to answer is, do those means all equal each other? Does that make sense? And you could compare mean 1 to mean 2, mean 1 to mean 3, and then mean 2 to mean 3, like all individually, right? But before that, what you could do is you could find the confidence intervals, or in doing so, find the confidence intervals for each mean. I think I showed you something like this from a Stanford study where there were 4 different diets, right? And there were confidence intervals for every single mean weight loss for all the diets, right? And if those confidence intervals overlapped, you couldn't conclude that those 2 groups were different, right? But if they didn't overlap, you conclude that they were different. Or you could use what else to compare 2 means at a time other than a confidence interval. What else do we do with comparing 2 means? You could do a hypothesis test. Does mean 1 equal mean 2, right? Or is mean 1 minus mean 2 equal to 0, right? That kind of thing. So, however, before you start testing pairs of things, something that you can do first is to carry out this significance test to tell if there are any differences among the populations being compared. And that test is called an ANOVA test, which is short for Analysis of Variance. And that's kind of the question it answers is, do the means vary? Is there a pair or 2 pairs where one is different than the other? And then once you know the answer to that question, yes or no, you can start looking for which pair is it. So it's kind of like first determine if there is a difference. and then find the pair or pairs. That's sad. Okay. All right, we'll give it 5 seconds. When we compare the means of populations represented by independent samples, I should say of a quantitative response variable, and a null hypothesis of interest is that all population means have the same value. The alternative is that the population means are not all equal. So for this case, your H naught is always going to be mean 1 equals mean 2 equals however many means you have. Could be 5, could be 10. I'll just say like up to mu n. And HA is that the population means are not all equal. Or there's at least one pair. And a common way to write that with this notation is mu I doesn't equal mu j for I not equal to j. That could be like mean 1 and mean 3 aren't equal, or mean 2 and mean 7. It's just saying there's some pair where they're not equal. Could be more than 1, 2, but at least one. That's all. And the statistic used to test this is the F statistic, which is the, well, you guys don't have this table, and we're not going to work with it at all, but there's another table called Table 8.4 that has F statistics in it. Just like you had chi-squared statistics, and you had T statistics, and you had Z statistics, right? There's also F statistics. And that is roughly speaking given by this conceptually. It's the variation between sample means divided by the natural variation between groups. And if your variation between your sample means is bigger than the natural variability that you expect, you're going to get bigger F statistics. And bigger F statistics are going to make littler p-values. Okay. So mostly I just care that you can like look at the computer output from an F test and tell me, can you reject H naught or accept, or do you fail to reject H naught? That's kind of all we're going to take from this. And then also just making sure you know when you can do this test. So the first thing is that the samples have to be independent random samples. So like in the example of the diet groups, you need to have 3 groups that are independent people. They can't be related somehow to each other. The distribution of the response variable is in a blank curve within each population. What do you think that has to be? Bell, yep. And also you have to assume that all populations have the same standard deviation. And one other thing, your response variable has to be quantitative. Not categorical. Okay. So first let's talk, could we have used an F test for these things? So we have a researcher and they're comparing the mean blood pressures of men over 50 years old for 3 different ethnic groups. He samples 100 men in each group and then he measures their blood pressures. So your 3 groups have to be independent. If they're different ethnic groups, you're probably not going to have people that are related in the different groups, right? Bell-shaped, would blood pressure probably be bell-shaped? I see no reason why not, right? And then also same standard deviation in each group? Probably, right? So in this case, yeah, it'd be appropriate. And is the response variable quantitative? Yeah, because blood pressure is quantitative. And we are comparing independent groups. Okay, how about this one? 50 individuals listen to 5 songs, and they rate each song on a scale of 0 to 100. And then the mean scores for the 5 songs are compared. So you have scores for every single song. Are the scores in group 1 independent from the scores in group 2? And I say no, and why not?
Because they're different songs.
They're different songs. I was thinking the same person rated them. Is your opinion about rock music related to your opinion about classical music? I would say for some people those things tend to go hand in hand. I don't know, I mean everybody, but yeah, if you like rock music, you may be more or less likely to not like something else. Does that make sense? So the kicker here is that since if you wanted to really rate these songs and do this test, you'd have to have 50 individuals listen to one song, 50 different individuals listen to the next song. Does that make sense? So there's not independence here because the same people listen to every single song. So, nope. The groups, or say the same person.
So it's like a bias.
Yeah, there's a bias introduced because potentially knowing something about a person could affect their response in every single group. Yeah. So how did I say this here? The groups are not independent.
Would this be bell-shaped as well or not?
I don't know. But I would expect people to have a variety of responses to songs, like you love it, you hate it, or, unless there's a song like the songs from Frozen, which we've all gotten over, Let It Go, where everyone hates it now. Since the same person, or same people, listen to all 5 songs. You'd have to have a really good reason to have something that was not bell-shaped. Does that make sense? Like, someone to tell you pretty much that was not the case for you to say that assumption was violated. An example, the best example of something that is not bell-shaped is house prices. Home prices are home prices. You tend to have lots of houses that are really, really, really expensive out on the far end, but home prices can't go negative, right? So there's lots of people that sort of have this median. That's why when you talk about home prices, like in the news, they say the median home price, because the median isn't affected by all these outliers. Look at you guys become good statisticians. It's so cute. But that is true. So if you listen to the news, they say, oh, the median home price has done blah, 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 right? They don't say the mean home price, they say median. And that's why. Because this data set is extremely skewed by people with lots of money and lots of expensive houses. Right? I mean, go to Minnesota and drive through Minnetonka and yeah, there's Prince's house behind a gate. I've bike packed there many times. No joke, really. Seriously, have. Okay. This is the kind of thing I care that you can do, though. Look at this little output from an analysis of variance thing. Okay, so here is the output from a researcher doing an experiment to compare the mean weight loss for 3 different programs for losing weight. And often to do this, you take your data and you put it into a program and it spits out some stuff for you because doing this by hand is really tedious. Okay, so your picture is bigger than mine. Can you find the F statistic? Where do you think it is? That's the 11.74. Where is the associated p-value? Exactly. And you see here we have program 1, 2, and 3. And there are all those little confidence intervals there. What do you think the starred value in the confidence interval is? The mean. And then you see that this tells you like just the interval, like what the range is from end to end, right? Based on these intervals, which programs appear to be different? 1 and 3, because they appear to have no overlap, right? Whereas 1 and 2 and 2 and 3 have overlap, right? Okay. So first of all, write null and alternative hypotheses for this problem. State that in words and in statistics. Okay, so H naught is that mean 1 equals mean 2 equals mean 3. Or in context, weight loss on average is the same for all programs. And HA, you can just go ahead and list in words. What is that?
It's not the same.
Mm-hmm. Weight loss is not the same.
So you wouldn't have to write that one with the,
I think it's too tricky, because it would be something like mu I does not equal mu j for I not equal to j. Because it could be mean 1 doesn't equal mean 2, or mean 2 doesn't equal mean 3, or mean 1 doesn't equal mean 3. It's like all these different pairs you could have. So don't worry about it for that one. I'll just check for the symbols in the H naught. Okay. What values are given in the output for the F statistic and the p-value? So F is 11.74, P is 0.006, and this p-value means the same thing it did in previous stuff. If the p-value is small, you reject the null hypothesis. So what do? You reject H naught, accept HA, as your p-value is less than 0.05. So weight loss is different for at least one pair of diets. And once you know that's true, you can start finding confidence intervals for every single diet, and then you can compare them all. Okay, so part C says, on the basis of the 95% confidence intervals given in that little table, describe the differences among the, I said age groups, I meant diet groups. So based on the intervals, which pair appears to be different? Yeah. Based on the 95% CIs, program 1 and program 3 seem to have different average weight losses. And it makes sense that program 2 is not statistically different from 1 or 3, right? And I think that was the same thing that was concluded with that diet I showed you, that study I showed you from Stanford, that the Atkins diet was different than one of the diets, but not the other two, because there was a teensy bit of overlap in the confidence intervals. Okay. And one thing that you have to assume in this is that you do have equal standard deviations. And you can see that there's this column here that gives ST-Dev for everybody. And this is a teensy bit borderline. Do you agree with that? Because this first standard deviation is just 1.6, 2.0, and then 3.0, right? So your book says that the biggest the difference can be is that the biggest one is twice the small one. Okay, so that, like, if the difference gets more than that, then maybe the standard deviations are different and that violation's been that assumption's been violated. Because there's always going to be variability. These are never going to be exactly the same. Does that idea make sense? So your book's rule of thumb for how much difference is too much difference is if the biggest one is more than twice the smallest one.
So if it was like 4.0.
If this were 4.0 and that was the 1.6, then yeah, probably the standard deviations are not all equal, right? But if this is just a little bit less than twice as much as that, right? So then we're okay. So what you should check here is twice the smallest, well, okay. So is 2 times the smallest standard deviation bigger than the largest? Okay. If so, maybe sigmas are different.
Would it be smaller than the largest standard deviation? If 2 times the smallest standard deviation.
If 2 times the smallest standard deviation is, oh, yes. Yeah, that should say smaller. Mm-hmm. You guys, you don't have to run away, seriously. I'm not quite done, and you're all 15 minutes early, so stop. It really is super annoying. I'm sorry, just end the semester, I'm easily irritated. If 2 times the smallest standard deviation is smaller than the largest, no, if that's, yeah, I think that was fine, but if it is smaller than the largest, if so, then, let's just change my conclusion. If so, then the sigma are probably the same. Crap. Distracted me. Okay, we're gonna bring out the white out. I'm sorry, you probably also wrote in pen. Like, I just did it and then can't write in words what I did. Okay, so if 2 times the smallest okay, in this case we just did 2 times our smallest standard deviation is bigger than, yeah, is bigger than the largest. You are okay. Just like we were here. Right, that's what we did here. Okay. If 2 times the smallest standard deviation is smaller than the largest, then probably sigmas are not the same.
So if they're not the same, can you still do that?
If they're not the same, you shouldn't do that F test. Yep. But in this case, we're still okay. Okay? So in this case, we're fine. Since 2 times that 1.633 is still bigger than 3.0. So we can assume the standard deviation sigma is the same for all groups. That's all.